there is a simple way to imagine the solar system that almost everyone learns first. The Sun sits at the center of the picture. Mercury circles close beside it. Venus comes next, then Earth, then Mars. Farther out are Jupiter, Saturn, Uranus, and Neptune, arranged like markers on a widening road. That picture is useful, but it hides the part that matters most when you try to cross the distance. The planets are never lined up and waiting. Each world is moving around the Sun at its own pace, following an orbit with its own size and shape. Earth moves continuously along its path. Mars does the same farther out. Venus moves more quickly on the inside. Neptune takes about 165 Earth years to complete a single revolution. So the distance from Earth to another planet is not one permanent number. It grows, shrinks, and grows again as two moving worlds change their positions around the same star. Astronomers make this easier to describe with a unit built from our own orbit. One astronomical unit, or 1 AU, is defined as 149,597,870.7 kilometers, a little under 93 million miles. It is close to the average distance between Earth and the Sun. From the Sun, Mercury orbits at roughly 0.39 AU, Venus 0.72, Earth 1, Mars about 1.52, Jupiter 5.2, Saturn about 9.5, Uranus a little over 19, Neptune about 30. Those numbers tell you where the planetary orbits lie. They do not tell you how far the planets are from you tonight. For that, you would need a moving map. Imagine for a moment looking down on the solar system from far above the plane of the planets. Earth is traveling around one path, while Mars moves around another. Sometimes, the two worlds occupy neighboring regions of their orbits. At other times, the Sun lies between them, and the separation becomes far greater. The same changing geometry applies to every other pair of planets, and a spacecraft cannot ignore that geometry. It does not leave Earth and simply aim at the place where another planet appears to be. By the time it crossed the intervening space, the target would have moved on. Interplanetary flight is therefore a problem of meeting a moving world at a future point in its orbit. Mission designers choose a launch time and a curved solar trajectory so that spacecraft and planet arrive at the same region of space together. One of the simplest idealized examples is the Hohmann transfer, an elliptical path connecting two orbits around the Sun. Real missions may use more complicated routes, gravity assists, course corrections, or different forms of propulsion. But the underlying idea remains. Crossing the solar system is not a straight road. It is an act of timing. That changes what the word distance means. There is the distance printed in a table. There is the changing separation between two planets. There is the length of the trajectory a spacecraft must actually fly. And there is another distance measured not in miles but in minutes, months, and years. Even light has to cross these spaces. From the Sun to Earth, the trip takes about 8 minutes and 20 seconds. Near Neptune's distance, light itself needs roughly 4 hours. To cross the space back toward us, no engine is involved in that delay. No fuel can shorten it. It is simply what separation becomes when information itself has a finite speed. So before traveling to any planet, it helps to set aside the idea of a fixed mileage. The solar system is not a collection of destinations pinned to a map. It is a moving arrangement of worlds, and every journey begins by learning where they will be when you arrive. Moving inward from Earth seems at first like the easier direction. Mercury and Venus lie closer to the Sun than we do. On the familiar diagram of the solar system, their orbits appear tucked neatly inside our own, and Mercury in particular can seem almost nearby. But orbital distance is not the same thing as travel difficulty. When a spacecraft leaves Earth for an outer planet, it must gain enough orbital energy to climb away from the Sun. To move inward, toward Venus or Mercury, it must do something that sounds easier but can be just as demanding. it must lose orbital energy. Earth is already moving around the Sun at almost 67,000 miles per hour. A spacecraft launched from Earth begins with that motion. It carries Earth's orbital speed with it. So reaching Mercury is not a matter of turning toward the Sun and allowing gravity to do the rest. Gravity will certainly pull the spacecraft inward. But as it falls, the spacecraft speeds up. By the time it reaches Mercury's region of the solar system, it can be moving far too quickly relative to Mercury to settle into orbit. The difficult part is not getting close. The difficult part is arriving slowly enough to stay. Mercury travels around the Sun in only 88 Earth days. Its average orbital distance is about 36 million miles from the Sun, but its orbit is noticeably elliptical. At different points in its year, Mercury moves between roughly 29 million and 44 million miles from the Sun. From Earth, the separation changes even more, but because both planets are moving, there are times when Mercury is tens of millions of miles away. At other configurations, it is well over 100 million miles from us. And neither of those straight-line figures tells you the length of the route a spacecraft will actually follow. The first spacecraft to orbit Mercury demonstrated this clearly. NASA's Messenger left Earth in August of 2004. Mercury is close enough that, in a simplified transfer calculation, a spacecraft can cross the radial distance between the two orbits in a matter of months. Messenger took more than 6.5 years. It did not spend those years simply coasting toward Mercury. Its path became a long sequence of carefully chosen encounters. It returned past Earth once, flew by Venus twice, and then past Mercury 3 times before finally entering orbit in March of 2011. Each encounter changed the spacecraft's trajectory. A gravity assist is sometimes described as taking free energy from a planet, but the deeper picture is a little more subtle. The spacecraft enters the planet's gravitational influence, curves around it, and leaves with its direction and speed relative to the Sun altered. The planet's own orbital motion becomes part of the exchange. For a mission to Mercury, those encounters can help remove the solar orbital energy that would otherwise have to be cancelled. With enormous amounts of propellant, the spacecraft travels farther in order to make arrival possible. That is one of the first strange lessons hidden inside planetary distance. The shortest looking destination may require the longer journey. Bepi Colombo, the European and Japanese mission now approaching Mercury, follows the same broad logic. It launched in October of 2018 and used a sequence of planetary flybys to reshape its orbit little by little. Its planned Mercury orbit insertion is in November of 2026, more than 8 years after launch. For most of that time, Mercury has never been difficult to locate. The challenge has been matching it, and when a spacecraft finally does, it reaches a planet shaped by its closeness to the Sun. Mercury has almost no substantial atmosphere to move heat around its surface. In sunlight, temperatures can climb to around 800 degrees Fahrenheit. During the long Mercurian night, exposed ground can fall to around -290. Those extremes exist on the same small world. Yet Mercury also contains places that almost never see the Sun at all. Near its poles, the floors of some deep craters remain in permanent shadow because Mercury's rotational axis is only slightly tilted. Radar observations and Messenger measurements have provided strong evidence for water, ice, inside some of those shadowed regions. A planet nearest the Sun can still preserve frozen water. Distance from the Sun matters, but geometry matters too. The next orbit outward belongs to Venus, and here the geometry changes again. Venus travels around the Sun at about 0.72 astronomical units. It is closer to Earth's orbit than Mercury is, and spacecraft can reach it relatively quickly. Several missions have made the trip in only a few months, but a short transit does not make Venus a simple destination. Venus is almost the same size as Earth. Its diameter is only slightly smaller, and its surface gravity is close enough to ours that a person standing there, if standing there were possible, would feel a familiar amount of weight. From a distance, the resemblance is striking. At the surface, it disappears. The Venusian atmosphere is dominated by carbon dioxide. Its surface pressure is roughly 90 times greater than Earth's sea level pressure. Its clouds contain sulfuric acid droplets, and the atmosphere traps heat so efficiently that average surface temperatures are around 870 degrees Fahrenheit. Mercury can become hotter in direct sunlight in some places. Venus remains intensely hot almost everywhere, day and night. That difference is created by atmosphere. Mercury receives far more solar energy, but with almost no air. Its surface can radiate heat away after sunset. Venus receives less sunlight, yet its dense carbon dioxide atmosphere holds heat within a powerful greenhouse system. Two neighboring planets, both closer to the Sun than Earth, produce completely different environments. And, once again, the mileage alone explains very little. The Soviet Venera probes gave humanity its first direct experience of the Venusian surface. Several survived long enough to transmit measurements, and a few returned photographs from beneath the clouds. Their working lives on the ground were measured in minutes rather than days. Venera 13, which landed in 1982, operated for a little over 2 hours. That brief survival was an engineering achievement because every system had to function while surrounded by crushing pressure and heat, capable of destroying ordinary electronics. The planet was close enough for radio signals to travel between Earth and Venus in only a few minutes, depending on orbital position. It was close enough for robotic spacecraft to reach in a fraction of a year, and yet its surface remains one of the most difficult places in the solar system for a machine to work for long. Mercury teaches that a nearby orbit can demand years of navigation before a spacecraft can settle into place. Venus teaches something different. Sometimes the journey is comparatively short, and the difficult distance begins only after arrival. These two inner worlds sit just across Earth's orbital neighborhood, visible from our sky, without any telescope at all. But between seeing a planet and reaching it lies an entire layer of physics that a simple map never shows. Beyond Earth, the geometry changes again. Mars is the first planet outward from our orbit, and because it appears so often in stories about future exploration, it can begin to feel almost nearby. Telescopes resolve its seasons, orbiters map its surface, rovers move across its plains. We receive weather reports from another planet, but familiarity can make distance feel smaller than it is. Earth and Mars circle the Sun on different tracks and at different speeds. Earth completes an orbit in 1 year. Mars takes nearly 2. Sometimes the two planets occupy the same general side of the solar system, with their separation reduced to tens of millions of miles. At other times, they are separated by the Sun and hundreds of millions of miles of space. A spacecraft cannot choose the shortest separation, simply because it would be convenient. It must leave when the orbital geometry allows its path to meet Mars months later. This is why launch opportunities to Mars recur, roughly every 26 months. The interval comes from the changing relationship between the two planetary orbits. Earth moves around the Sun more quickly, gradually catching Mars, passing through a useful alignment, then continuing ahead until the geometry returns again. The launch window is not an arbitrary date on a mission calendar. It is a consequence of two worlds moving through gravity. For many conventional Mars trajectories, the crossing takes something like 6 to 9 months. The exact duration depends on the launch vehicle, spacecraft, mission design, and positions of the planets. That is long enough for the spacecraft to travel a path far greater than the minimum straight-line separation between Earth and Mars. It is also long enough for Earth itself to move through a substantial portion of its orbit. By the time a spacecraft reaches Mars, the place it departed is no longer behind it in any simple sense. Earth has continued around the Sun. Mars has moved as well. The spacecraft has spent those months following a third orbit of its own, one designed to intersect Mars at the correct moment. The destination is not merely a place, it is an appointment. There is something useful in picturing the journey this way. Imagine Earth at departure as one moving point on a great circular track. Farther out, Mars is another. Between them is not an empty road, but a region dominated by the Sun's gravity. The spacecraft leaves Earth and becomes for a time another small object orbiting the Sun. It does not travel independently of the solar system. It joins its motion. That fact helps explain why Mars missions can wait so long for another favorable return opportunity. A crew arriving on Mars cannot always turn around and take the same path home. Earth will not be where that return path needs it to be. One common class of crewed mission concepts, therefore, includes a long stay on Mars while the planets move toward another favorable alignment. The total expedition can extend for years, even though the one-way crossing may take only several months. Distance becomes schedule. Schedule becomes life support, stored food, spare parts, radiation protection, crew health, and the ability to solve problems. Without immediate assistance from home, even communication begins to change character. A radio message cannot cross the Earth-Mars gap instantly. Depending on where the planets are, a one-way signal may take only a few minutes, or roughly 20 minutes. That means a conversation cannot behave like an ordinary conversation. A question sent from Mars may arrive on Earth after the situation that produced it has already changed. A response must then cross the same distance in the opposite direction. For robotic missions, engineers work around this by sending carefully prepared commands and allowing spacecraft considerable independence. A rover does not receive continuous steering from a person holding a control stick on Earth. It is given instructions, carries them out, evaluates some local conditions for itself, and later reports what happened. Mars is close enough that we can communicate with it every day. It is far enough that we cannot be present in real time. The planet itself reinforces that separation. Mars has only about 38% of Earth's surface gravity. Its atmosphere is thin, dominated by carbon dioxide, and its surface pressure is less than 1% of the pressure most people experience near sea level on Earth. The atmosphere is thick enough to make weather. Clouds form, winds move dust. Large storms can spread across enormous regions and on occasion obscure much of the planet, but the air is far too thin to breathe and too thin to provide the kind of protection Earth's atmosphere gives us. Temperatures vary widely with location, season, elevation, and time of day. A sunny afternoon near the equator can become relatively mild by Martian standards. Elsewhere, and especially at night or toward the poles, temperatures fall far below anything encountered in ordinary terrestrial weather. Radiation presents another difference. Earth is protected by a thick atmosphere and a global magnetic field. Mars has neither in the same form. Its global magnetic field disappeared early in the planet's history, leaving localized crustal magnetic regions instead. Its thin atmosphere provides much less shielding from energetic particles arriving from space. For robotic explorers, these conditions are engineering constraints. For people, they would become part of the daily environment. A human journey to Mars would therefore not be defined simply by surviving 7 months inside a spacecraft and then opening a hatch. The spacecraft would remain part of a larger chain of protection that could never be casually abandoned. Habitats, power systems, pressure vessels, water reserves, thermal control, radiation shelters, suits, communications equipment, and machinery for producing or storing consumables would all stand between a crew and an environment that offers almost none of the conditions the human body expects. And yet Mars remains more accessible than the worlds beyond it. Its solid surface can be reached. Sunlight is still strong enough to be useful. A Martian day lasts only a little longer than an Earth day. Water ice exists in the subsurface and at the poles. The atmosphere, though thin, contains carbon dioxide that can be processed chemically. NASA's Perseverance rover carried a small experiment called MOXIE that demonstrated one part of this possibility by producing oxygen from carbon dioxide in the Martian atmosphere. It was not a life support plant for a settlement. It was a demonstration that material already present on Mars can be transformed into something a future mission may need. That distinction matters because carrying everything from Earth is one of the hidden costs of distance. Every kilogram of food, water, oxygen, shielding, equipment, and spare hardware must first be lifted away from Earth, then accelerated onto an interplanetary trajectory. The more a mission can obtain or manufacture at its destination, the less it may need to carry across the space in between. Mars, therefore, becomes the first planet where distance is not only a question of transportation, it becomes a question of independence. Then, beyond Mars, the solar system opens. Between the orbit of Mars and the orbit of Jupiter lies the main asteroid belt. In illustrations, this region is often shown as a crowded band of rocks. From that picture, it is easy to imagine a spacecraft weaving between boulders, constantly avoiding collisions. The real belt is almost the opposite. It contains enormous numbers of asteroids, but they are distributed across an immense volume of space. Spacecraft have crossed the region repeatedly without navigating anything like the obstacle course shown in fiction. The belt is wide, sparse, and mostly empty. Its objects are remnants from the early solar system, pieces of material that never became part of a full-sized planet. Some are rocky, some contain large amounts of metal. Others preserve carbon-rich material or water-bearing minerals that offer clues to conditions during planetary formation. The largest object there is Ceres, a dwarf planet about 940 kilometers across. Ceres alone contains a substantial fraction of the belt's mass, yet even it is tiny beside Earth. The asteroid belt is therefore not a wall separating the inner and outer planets. It is more like a long transition. Behind you are the small, rocky worlds, Mercury, Venus, Earth, and Mars. Ahead lies Jupiter, and with Jupiter, the scale changes. The distance from the Sun suddenly expands from Mars at about 1.5 astronomical units to Jupiter at more than 5. For the first time on this outward journey, the gap between neighboring planetary orbits becomes larger than the entire region, containing several of the planets already crossed. The solar system begins to spread out, and the next world is no longer measured comfortably in months alone. Jupiter changes the scale of the journey. Mars moves around the Sun at about 1.5 astronomical units. Jupiter travels at more than 5. Between those two orbits lies a span of space wider than the entire region from the Sun to Mars. From Earth, the distance to Jupiter is never fixed. When the two planets occupy favorable parts of their orbits, they can be separated by a little more than 360 million miles. When they lie on opposite sides of the Sun, the gap can grow beyond 600 million. But once again, a spacecraft does not simply cross the shortest line between them. It follows an orbit around the Sun. A minimum energy transfer from Earth's orbit toward Jupiter takes on the order of 2 years and 8 months. Actual missions can be faster or slower because mission designers trade among launch energy, spacecraft mass, gravity assists, fuel reserves, and the conditions required at arrival. NASA's Juno spacecraft, for example, left Earth in August of 2011 and and reached Jupiter in July of 2016. Its journey lasted almost 5 years. Juno did not spend those years moving directly outward. After launch, it entered an orbit around the Sun that eventually brought it back past Earth in 2013. Earth's gravity altered the spacecraft's speed and direction, giving it the additional energy needed for the long climb toward Jupiter. For a moment, a spacecraft bound for the outer solar system came home before leaving for good. Then Earth began to diminish behind it. The Sun diminished too. At Jupiter, sunlight is only a small fraction of its strength at Earth. Yet, Jupiter itself dominates the region so completely that arrival does not feel like reaching one isolated planet. It feels like entering another system. Jupiter is more than twice as massive as all the other planets combined. Its gravity governs a large family of moons, rings, charged particles, dust and magnetic structures, extending far into surrounding space. The planet has no solid surface where a spacecraft could simply land. What we call Jupiter's surface is really a visible layer of clouds. Below those clouds, pressure rises continuously. Hydrogen gas becomes denser, then behaves increasingly like a fluid. Farther down, under pressures difficult to reproduce on Earth, hydrogen enters a metallic state capable of conducting electricity. There is no clean boundary where sky becomes ground. A descending vehicle would move deeper into atmosphere until pressure and temperature destroyed it. Jupiter is therefore a destination that can be approached, orbited, sampled from above, and studied remotely, but not stood upon. And the farther you move into its neighborhood, the more another feature of the planet becomes important. Jupiter possesses the strongest planetary magnetic field in the solar system. That field traps charged particles and accelerates them into powerful radiation belts. For robotic spacecraft, radiation gradually damages electronics and sensors. Mission designers shield vulnerable components, select resistant hardware, and plan trajectories that limit the time spent in the harshest regions. Juno carries many of its sensitive electronics inside a titanium vault. Europa Clipper uses its own radiation protection strategy because its destination lies deep within the same environment. Distance has brought the spacecraft far from Earth. Jupiter adds another boundary after arrival. Some of its most interesting worlds sit inside a region where merely remaining nearby is difficult. The 4 largest moons were first observed by Galilei in 1610. Io, Europa, Ganymede, and Callisto appeared as small points, changing position from night to night. Their movement around Jupiter provided visible evidence that not everything in the sky revolved around Earth. More than 4 centuries later, those same 4 points have become worlds. Io, the innermost of them, is a place almost continually remade by geology. Its orbit is influenced by Europa and Ganymede in a repeating gravitational rhythm. Their combined pulls keep Io's orbit slightly non-circular. As Io moves around Jupiter, the strength of Jupiter's gravitational pull changes enough to flex the moon's interior. Rock bends. Friction produces heat. That heat escapes through volcanoes. Io is the most volcanically active known world in the solar system. Its surface is covered by lava flows, volcanic deposits, mountains, and regions that can change noticeably between spacecraft observations. The energy driving those eruptions does not come mainly from sunlight. It comes from motion and gravity. Farther out is Europa. From a distance, Europa looks calmer. Its surface is bright ice crossed by long fractures and darker bands. Large impact craters are relatively scarce, suggesting that the surface has been renewed over geological time. Beneath that ice, multiple lines of evidence point toward a global ocean of salty liquid water. The amount of water may be greater than the water contained in all of Earth's oceans combined. That possibility changes Europa from an icy moon into one of the central destinations in planetary science. Liquid water is only part of the question. Scientists also want to understand the chemistry of the ocean, the nature of the rocky material beneath it, the energy available there, and whether material can move between the surface and deeper layers. Europa is not assumed to contain life. The scientific question is whether it contains conditions that could support it, and studying that question requires repeatedly entering Jupiter's radiation environment. Europa Clipper launched in October of 2024. Its route to Jupiter covers about 1.8 billion miles because the spacecraft follows a long gravity-assisted trajectory rather than a straight line. It is scheduled to reach Jupiter in April of 2030. After arrival, it will orbit Jupiter rather than Europa itself. That choice is partly a response to radiation. A tight orbit around Europa would expose the spacecraft continuously to damaging charged particles. By following a stretched orbit around Jupiter, Europa Clipper can pass close to the Moon for observations, and then spend much of each orbit farther from the most punishing region. The plan includes 49 close flybys. A moon, a world only a few thousand kilometers across, requires a planetary scale orbit merely to make repeated observations survivable for the spacecraft. Beyond Europa comes Ganymede. It is the largest moon in the solar system, larger in diameter than Mercury. Ganymede also has something no other moon is known to possess: an internally generated magnetic field. Beneath its surface, there is strong evidence for another salty ocean, perhaps arranged within a complicated interior, containing alternating layers of liquid water and high-pressure forms of ice. The pattern continues. A moon that once looked like a point of light becomes a layered planetary body with its own geology, magnetic environment, and hidden water. Then comes Callisto, the outermost of the four. Its surface carries scars accumulated across immense spans of time. Craters, overlap craters, recording impacts that younger or more active worlds have erased. Callisto orbits farther from Jupiter's strongest radiation belts than Io, Europa, or Ganymede. That relative distance has made it interesting in some studies of possible future human exploration. Although sending people anywhere near Jupiter remains far beyond current crewed capability. Even here, distance is layered. First, there is the journey from Earth to Jupiter. Then, there are the distances within the Jovian system itself. Io orbits hundreds of thousands of miles from Jupiter. Europa lies farther out, Ganymede farther still. Callisto travels at nearly 2 million kilometers from the planet. The space occupied by Jupiter and its large moons is itself comparable to a miniature planetary system, and communication with Earth has become noticeably slower. Depending on the positions of Earth and Jupiter, a radio signal generally needs around half an hour to nearly an hour to make the trip one way. If a spacecraft encounters a problem, controllers cannot observe it and respond immediately. The spacecraft may transmit information describing what has happened. That information crosses hundreds of millions of miles. Engineers study it on Earth. Their response crosses the distance back. By then, more than an hour may have passed. This is why distant spacecraft are built with some ability to protect themselves. They monitor critical conditions. They can enter safe modes. They can stop normal operations and wait for instructions when something falls outside expected limits. Autonomy is not a luxury added to a deep space mission. It grows naturally out of separation. There is a human history hidden inside that delay. Galileo watched Jupiter through a small telescope and drew the changing positions of 4 lights by hand. Centuries later, teams on Earth send commands toward machines moving among those same moons. The tools have changed almost beyond recognition. The waiting has not disappeared. A command leaves an antenna on Earth and becomes a radio wave moving outward. For a while, there is nothing anyone can do to make it arrive sooner. The signal simply crosses. If you are resting beneath Earth's sky while that happens, Jupiter may appear as one bright point among the stars. No visible gap reveals the hundreds of millions of miles between here and there. The distance is hidden inside the travel time of the light, and Jupiter is only the first of the giant planets. Beyond Callisto, beyond the outer, beyond edges of Jupiter's magnetic domain, there is still another immense crossing before the next major world begins to gather sunlight into rings. By the time you reach Saturn's orbit, the Sun has changed. It is still unmistakably a star, still bright enough to illuminate planets and rings, but the sunlight falling there is only about 1% as intense as the sunlight reaching Earth. Saturn moves around the Sun at roughly 9.5 astronomical units. One complete Saturnian year lasts almost 29.5 Earth years. So even before considering a spacecraft, the rhythms of this part of the solar system are becoming longer. A season on Saturn lasts for years. A single orbit spans a large portion of a human working life, and the space between Earth and Saturn changes continuously as both planets move around the Sun. There is no permanent Earth to Saturn mileage. Sometimes the planets occupy the same general side of the solar system. Sometimes the Sun lies between them. A spacecraft must enter that moving geometry and follow a trajectory that intersects Saturn's orbit when Saturn itself arrives there. Cassini provides one of the clearest examples of what that really means. The spacecraft left Earth in October of 1997. It did not point towards Saturn and simply accelerate outward. Instead, Cassini passed Venus twice, returned past Earth, and later flew by Jupiter. Each encounter reshaped its solar orbit and helped provide the energy required to move farther outward. By the time Cassini reached Saturn in July of 2004, nearly 7 years had passed since launch. Its interplanetary route had covered billions of miles. The destination that appears as a pale point in Earth's night sky had required an itinerary through several planetary neighborhoods before the spacecraft could finally slow into orbit around it. For people living long before rocket, Saturn represented a different kind of limit. It is visible without a telescope, and for much of recorded history, it was the most distant planet anyone knew existed. Ancient sky watchers could follow its gradual movement against the background stars without knowing what the light actually was. Saturn moves so slowly across the sky that its wandering can be followed over years. Generations observed the same pale object. Only after the telescope appeared did the point begin to unfold into a system. Galileo saw something strange beside Saturn in 1610 but could not resolve the structure clearly. Later observers, using better instruments, recognized the rings. Today, spacecraft images have made those rings familiar enough that it can be easy to forget their scale. The main ring system stretches hundreds of thousands of kilometers from side to side, yet much of it is remarkably thin compared with its width. The rings are not solid sheets. They are made of countless individual pieces, most dominated by water ice, ranging from tiny grains to much larger blocks. Each piece follows its own orbit around Saturn. From far away, that population becomes a continuous band. From within the system, it is orbital mechanics repeated, but across an enormous number of particles. Small gravitational differences organize the rings into gaps, waves, edges, and narrow structures. Saturn's moons disturb them. Particles collide. Resonances redistribute material. The result is less like a decorative disk surrounding a planet, and more like a vast physical experiment in gravity. Cassini spent 13 years inside that experiment. That duration matters. A flyby can reveal a world. An orbiter can watch it change. Cassini observed Saturn through changing seasons. It followed storms. It watched shadows move across the rings as Saturn advanced around the Sun. It repeatedly visited moons instead of seeing them only once. and every one of those observations had to travel back to Earth across more than 1 billion kilometers of space. Depending on where the planets were in their orbits, radio signals took well over an hour to travel one way between Saturn and Earth. The spacecraft, therefore, lived in a different operational tempo from anything close. To home, commands were prepared in advance. They crossed the solar system. Cassini carried them out later. Scientific data then began the long return journey toward Earth. There was no possibility of seeing an unexpected event and immediately taking control. Mission planners had to anticipate. The spacecraft had to endure, and sometimes the most valuable discoveries emerged from observations designed for something else. One of those discoveries involved a moon so small that it might easily have seemed secondary beside Saturn and Titan. Enceladus is only about 500 kilometers across. Its surface reflects large amounts of sunlight because it is coated in fresh ice. Before Cassini, scientists had reasons to suspect that something unusual might be happening there. But the scale of the activity was not known. Then Cassini found jets erupting from fractures near the moon's south pole. Water vapor and icy particles were escaping into space. The spacecraft flew through the plume. Inside that material were salts, organic compounds, molecular hydrogen, and tiny silica particles that provided evidence about bankages far below the surface. The emerging picture was of a global salty ocean beneath the ice. Water from that ocean interacts with rock. Hydrothermal processes appear to occur on the seafloor, and cracks in the outer shell provide a route by which some of that material reaches space. This makes Enceladus unusual among possible places to search for habitable conditions. Its ocean is hidden, but some of the ocean comes to us. A future spacecraft would not necessarily need to drill through kilometers of ice simply to sample material that has been in contact with the subsurface water. It could pass through the plume and collect particles already escaping from the moon. Distance still imposes the larger problem. To sample that material with a new mission, another spacecraft must be designed, funded, built, launched, and sent across the same immense region Cassini crossed. The scientific target may be accessible locally. The Saturn system itself is not. Farther out among Saturn's moons is Titan. Titan is larger than Mercury, and it possesses a dense atmosphere, mostly made of nitrogen. At the surface, the pressure is greater than Earth's sea level pressure. The temperature, however, is around negative 290 degrees Fahrenheit. Water there behaves more like rock than liquid. Methane and ethane can behave like water does on Earth. They form clouds, they fall as rain, they collect in lakes and seas. They carve channels across the landscape. Titan therefore has something that feels strangely recognizable at the level of process, while remaining alien in material. There is weather, there are shorelines, there are dunes, there is a cycle of evaporation, condensation, precipitation, and flow. But the liquid moving through that cycle is not water. Cassini carried a smaller spacecraft specifically for Titan. The European Space Agency's Huygens probe separated from Cassini and descended through Titan's atmosphere in January of 2005. Its parachutes opened beneath the orange haze. For more than 2 hours, instruments sampled the atmosphere while cameras watched the surface draw nearer. Huygens eventually landed among rounded pieces of water ice on terrain shaped by flowing liquid. It remains the most distanced landing ever performed by a human-built spacecraft. For a brief period, a machine built on Earth sat on a world more than 1 billion kilometers from home and transmitted measurements upward through Titan's atmosphere. The transmission could not be answered in real time. By the time the information reached Earth, the events it described were already long over. Yet the delay did not make the measurements less useful. This is one of the habits planetary exploration slowly teaches. At great distance, knowledge often arrives as history. You learn what the spacecraft encountered after the encounter has happened. You see the descent after the probe has already landed. You receive the final signal from a fission after. The spacecraft that sent it can no longer exist. Cassini's own ending carried this character. By 2017, its propellant reserves were becoming limited, and engineers did not want an uncontrolled spacecraft, eventually striking Enceladus or Titan, because both moons are important to questions about habitability and had to be protected from accidental terrestrial contamination. So, Cassini's final trajectory was deliberately directed into Saturn. On September 15, 2017, the spacecraft entered the upper atmosphere while transmitting data. Atmospheric drag increased. Attitude control systems fought to keep the antenna pointed toward Earth. Eventually, the spacecraft could no longer maintain contact. Its final radio signal continued traveling after Cassini itself had been destroyed. Earth received the end later. For the people watching the signal on their screens, that delay had become part of the meaning of the mission. The spacecraft had spent years teaching them to work across a gap that could never be closed. Another machine is being prepared to make the crossing. NASA's Dragonfly mission is scheduled to launch no earlier than July of 2028 and reach Titan late in 2034. Dragonfly is not designed to roll slowly across one patch of terrain. It is a rotorcraft. Titan's dense atmosphere and low surface gravity make powered flight unusually useful there. Dragonfly is intended to land, study one location, then fly to another, carrying its laboratory across the landscape. It will examine Titan's chemistry, geology, atmosphere, and environments where complex organic material and water may have interacted. The flight from one site to another may take minutes. Reaching the moon where those flights will happen requires years. That contrast is becoming familiar now. Inside a distant planetary system, movement can be manageable. The difficult crossing is the one that connects that system to Earth. Saturn therefore marks more than another stop on an outward map. It is where long-duration exploration begins to become normal. 7 years to arrive can be followed by more than a decade of science. A mission can begin with one generation of technology and remain active long enough for the world on Earth to change around it. And beyond Saturn, even that scale starts to stretch again. The next planet lies so far from the Sun that it has completed fewer than 3 full orbits since William Herschel first recognized it as a planet in 1781. Its name is Uranus, and reaching it has happened only once. Uranus begins another scale of distance. Its orbit lies about 19 astronomical units from the Sun, roughly twice Saturn's distance. 1 Uranian year lasts about 84 Earth years. A person could be born, grow old, and live an entire lifetime, while Uranus completes only one circuit around the Sun. And from Earth, reaching it has happened only once. Voyager 2 left Earth in August of 1977. After passing Jupiter and Saturn, it continued outward for years, following a trajectory made possible by the arrangement of the giant planets. It reached Uranus in January of 1986, more than 8 years after launch. The closest encounter lasted only hours. For that brief interval, a spacecraft crossed a region no human-built machine had ever visited. Cameras recorded the planet, its rings, and its moons. Instruments measured magnetic fields, particles, temperature, and atmospheric structure. Then Voyager 2 continued on. No spacecraft entered orbit around Uranus. None remained there to watch a full season change. The only close examination humanity has ever made of the planet was performed by a machine moving past it on the way to somewhere even farther away. That limitation shapes nearly everything we know about Uranus. From Earth and from telescopes in space, astronomers can continue observing it. They can track clouds, measure atmospheric chemistry, study its rings, and refine models of its interior. But remote observation and close observation answer different kinds of questions. A telescope can reveal what light does after leaving a planet. A spacecraft can move directly through the surrounding magnetic field, sample charged particles, map small moons at much higher resolution, and watch the planet from changing angles over years. Uranus has never received that second kind of attention for more than a passing encounter. And the world Voyager revealed was already difficult to fit into the pattern established by Jupiter and Saturn. Uranus rotates almost on its side. Its axis is tilted by about 98 degrees relative to its orbit. Instead of spinning like a top that is roughly upright as it circles the Sun, Uranus rolls around its path, with its poles sometimes aimed almost toward the Sun. Because its year lasts 84 Earth years, this produces seasons that unfold across decades. Near a solstice, one polar region can remain directed toward the Sun for years, while the other faces away. Then, over decades, the geometry reverses. A human observer could not simply spend a few months there and watch a complete seasonal cycle. To observe Uranus through all 4 seasons would require a scientific program lasting longer than many careers. Its magnetic field is unusual as well. The field is strongly tilted relative to the planet's rotation axis and displaced from the center of the planet. As Uranus rotates, the surrounding magnetosphere changes orientation in a complicated way. If you could see magnetic fields with your eyes, the space surrounding Uranus would not resemble a simple symmetrical bubble. It would appear to twist and change as the planet turned. Its interior presents another puzzle. Jupiter radiates more energy than it receives from the Sun. Saturn does too. Neptune, farther away, also releases substantial internal heat. Uranus emits far less excess heat. Why 2 planets as broadly similar as Uranus and Neptune should behave so differently remains an open problem. One possibility is that the structure inside Uranus prevents heat from moving outward efficiently. Another is that events early in the planet's history changed the way its interior evolved. The evidence does not yet provide a complete answer. Distance slows the process of finding one. The same is true for Uranus's moons. Miranda was one of Voyager's surprises. Its surface includes enormous fault scarps, ridges, fractured regions, and terrain that appears assembled from different geological histories. Some landscapes look as though large portions of the moon were broken, shifted, and resurfaced. Voyager saw them from a passing trajectory. That was enough to reveal the question. It was not enough to settle it. A distant world can remain scientifically active in this way for decades. The data arrives once. Researchers examine it repeatedly. Better models appear. New telescopes add measurements from Earth. But the decisive next observation may require another spacecraft to cross billions of miles. So the distance to Uranus is not only the time needed to arrive, it can become the time between generations of evidence. Then comes Neptune. There is no planet beyond it. Neptune circles the Sun at about 30 astronomical units, around 30 times Earth's distance from the Sun. A Neptune year lasts almost 165 Earth years. Since its discovery in 1846, Neptune has completed only a little more than 1 full orbit. Human astronomy has known the planet for less than 2 Neptunian years. Voyager 2 reached it in August of 1989. 12 years had passed since the spacecraft left Earth. The machine that arrived at Neptune had been designed, assembled, and launched in the 1970s. By the time its final planetary encounter began, Earth had moved through an entire era of technology and culture. Neptune had barely moved through a small fraction of 1 season. Voyager's cameras found a blue planet with an atmosphere far more active than its great distance from the Sun might suggest. Clouds moved through the upper atmosphere. Large storm systems appeared. Winds reached speeds greater than those measured on any other planet. This seems surprising at first, because Neptune receives so little sunlight. At 30 astronomical units, solar energy is greatly reduced compared with Earth. But Neptune also releases internal heat. Energy rising from the planet's interior contributes to the motions of its atmosphere, helping drive weather on a world where sunlight alone might seem too weak to produce such activity. During Voyager's encounter, one enormous storm became known as the Great Dark Spot. Years later, when the Hubble Space Telescope observed Neptune, that particular feature had disappeared. Other dark storms have appeared and faded since. This tells us that Neptune is not a planet with one permanent pattern of clouds waiting to be photographed again. Its atmosphere changes, and because Voyager passed only once, humanity never had a spacecraft nearby to watch the Great Dark Spot form, evolve, and vanish. The distance turned a dynamic weather system into a handful of observations separated by years. Neptune's largest moon makes the story stranger. Triton travels around Neptune in the opposite direction from the planet's rotation. Most large moons orbit their planets in the same general direction. The planets rotate. Triton's retrograde motion is strong evidence that it did not form in place with Neptune. The leading explanation is that Triton originated elsewhere in the outer solar system and was captured by Neptune's gravity long ago. Capture would have transformed the Neptune system. Triton's original orbit was probably far less circular than the orbit we see today. Gravitational interactions and tidal forces would have dissipated energy over time, reshaping both Triton and the arrangement of any moons that were already present. Today, Triton is one of the coldest surfaces ever visited by a spacecraft, yet Voyager saw signs of activity there. Dark plumes rose several kilometers above the surface. They appear to be driven by nitrogen ice responding to the weak sunlight that reaches Triton. Even at the edge of the planetary system, where the sun looks much smaller than it does. From Earth, a little absorbed energy can still move material and create visible change. A moon at nearly 30 astronomical units is not completely frozen into geological inactivity. It still responds. It still changes. And we saw that activity during one encounter in 1989. No spacecraft has returned to Neptune since. The planet, Triton, its rings, its smaller moons, its magnetic field and its atmosphere have therefore never been studied by a dedicated orbiter. For more than 3 decades, every new close view of Neptune has had to come from telescopes observing across the full distance from our part of the solar system. That distance is large enough for light itself to require several hours to cross it. A radio command sent toward a spacecraft near Neptune would continue outward long after the transmission ended on Earth. During that time, nothing could accelerate the message. Nothing could call it back. It would move at the speed allowed by nature, crossing millions of miles every minute and still requiring hours to arrive. A response would need the same kind of journey in reverse. If you were beside Neptune while a message from Earth was on its way, Earth would not be present as a live voice. It would be a source of information separated from you by time. The planet visible through the window would be immediate. The people at home would be hours away, even when neither side had moved at all. There is no failure of engineering in that delay. The antennas could become larger, signals could carry more information, computers could become faster. The gap itself would remain. At Uranus and Neptune, the solar system begins to reveal a form of distance that cannot be reduced simply by building a better engine. The spacecraft may someday travel faster. The message will not. The spacecraft may someday travel faster. The message will not. That difference becomes one of the defining facts of deep space travel. Radio waves and laser signals move at the speed of light, about 300,000 kilometers every second. Across ordinary human distances, that speed feels instantaneous. A phone call can cross an ocean with only a small delay. A satellite in low Earth orbit can exchange data with ground stations in fractions of a second. But the solar system is large enough to make even light take time. From Mars, a message may need only a few minutes to reach Earth when the planets are relatively close. At other times, it can take more than 20 minutes one way. Near Jupiter, the delay is measured in tens of minutes. From Saturn, it stretches beyond an hour. Uranus pushes it into multiple hours. Near Neptune, a one-way signal can spend roughly 4 hours crossing interplanetary space. Nothing is wrong with the transmitter. Nothing is wrong with the receiver. The distance itself is doing the delaying. For robotic spacecraft, this creates a particular style of exploration. A rover on Mars cannot be driven the way a remote-controlled car is driven in a backyard. By the time an image showing a hazard reaches Earth, the rover has already been sitting beside that hazard for minutes. A steering command sent back will require more time to arrive, so the machine must be given a plan rather than a continuous hand on the controls. It receives instructions. It evaluates some conditions locally. It carries out a sequence of actions. Later, Earth learns what happened. The farther outward you go, the more the independence becomes part of the design. At Neptune, there is no meaningful version of real-time control from Earth. If a spacecraft detects a serious problem, its onboard systems must first keep it alive. Engineers can analyze the data and prepare a response, but the spacecraft must survive long enough for that response to cross billions of kilometers. This is one reason deep space missions use safe modes. When something unexpected happens, a spacecraft may stop normal science operations, reduce activity, orient itself into a safer configuration, maintain power and temperature, and wait. Waiting is an engineering function. It is built into the machine because the people who know how to help are far away. For a human crew, the same physics would become more personal. Near Earth, astronauts can speak with mission control almost as a live conversation. Questions can be answered quickly. Medical teams can advise. Engineers can watch telemetry, while the crew describes what they are seeing. On Mars, that relationship changes. A crew could report a malfunction, and then spend many minutes solving it, but before Earth even hears the first description. If the problem is urgent, the response from home may arrive only after the crew has already made the important decisions. Farther out, this separation becomes larger still. At Saturn, a question and answer could take hours. At Neptune, a complete exchange could occupy much of a waking day. By then, Earth is no longer functioning as immediate support. It becomes a distant partner. The crew has to become the local mission control, the medical team, the repair department, and the final authority for whatever cannot wait. Distance changes the social structure of exploration. It also changes the body. Beyond Earth's atmosphere and magnetic protection, people are exposed to a radiation environment unlike the one at the surface of our planet. Two broad sources matter. One is the sun. Solar eruptions can accelerate large numbers of energetic particles into space. If a spacecraft lies in the path of a strong event, radiation levels can rise quickly. The other source comes from far beyond the solar system. Galactic cosmic rays are high-energy atomic nuclei that arrive from many directions. Some were accelerated by powerful events in the galaxy long before they reached our neighborhood. In interplanetary space, passing through spacecraft, equipment, and human tissue, Earth protects us in ways that are easy to forget. The atmosphere provides a thick physical barrier. The magnetic field redirects many charged particles before they can reach lower altitudes. Together, they make the surface a very different radiation environment from open space. A crew traveling between planets loses much of that protection. Shielding helps, but shielding in space is complicated. You could simply imagine adding more metal around the crew compartment. yet high-energy particles. Striking heavy materials can produce secondary particles, creating additional radiation inside the vehicle. Materials rich in hydrogen, such as water and certain plastics, can be useful because they interact with incoming particles differently. This is one reason mission concepts sometimes place water, food, or other supplies around areas where the crew may shelter during a solar particle event. The supplies become part of the spacecraft's protective architecture. Even so, there is no simple wall that makes a multi-year interplanetary journey equivalent to living on Earth. Radiation accumulates over time, and time is exactly what long-distance travel requires. This connects the outer solar system to another problem that is less dramatic but equally persistent. The human body evolved under gravity. When gravity is greatly reduced for long periods, muscles weaken unless they are exercised. Bones lose mineral, the cardiovascular system adjusts. Fluids shift toward the head. Balance and coordination change. Astronauts in orbit work against these effects every day with carefully planned exercise, but countermeasures do not make long-duration weightlessness biologically invisible. For a journey to Mars, these changes would unfold over months. For a slow journey to the outer planets, they could unfold over years. Then the crew would arrive not at another Earth, but at a place with different gravity, different radiation, different temperatures, and no natural environment compatible with human life. The challenge is therefore not just surviving the destination, it is arriving in condition to work there. One possible answer is artificial gravity. A spacecraft or habitat could rotate so that occupants experience an outward acceleration against the interior wall. In principle, this can imitate some effects of gravity. The physics is straightforward. The engineering is not. A large rotating structure adds mass, complexity, mechanical demands, and design constraints to a vehicle that must already carry propulsion, shielding, life support, power systems, supplies, instruments, and redundancy. Every solution becomes another thing that must be launched and accelerated. This brings distance back to the rocket. The farther you want to travel, or the faster you want to arrive, the more energy you need to change your trajectory. Chemical rockets are powerful enough to lift large vehicles from Earth and send spacecraft throughout the solar system. But they consume propellant quickly. They are best at producing strong thrust for relatively short periods, not at pushing a heavy crewed spacecraft continuously for years. Other propulsion methods can trade thrust for efficiency. Electric propulsion, for example, can accelerate charged particles to very high exhaust speeds while using far less propellant than a chemical engine. The thrust is small, but it can continue for long periods. For robotic spacecraft, that can be extremely useful. A tiny continuous push, applied for months, can gradually reshape an orbit in ways a short chemical burn cannot. For human travel, reducing transit time creates different priorities. A faster journey can mean less time exposed to radiation, less time in reduced gravity, fewer months of stored consumables, and less psychological isolation. Speed becomes a form of protection, but speed has to be purchased with energy, propellant, mass, or some combination of all three. There is no single number called the cost of going to another planet. The cost changes with the route. It changes with how quickly you want to arrive. It changes with whether you need to orbit, land, return, or carry people. It changes with how much shielding, food, water, redundancy, and living space you decide is necessary. A robotic flyby can accept one set of compromises. A crewed round trip requires another, and this is why the straight-line distance between planets is such an incomplete measure. A destination may be only a few 100 million miles away and still demand years of preparation, months of exposure, precise launch timing, autonomous decision-making, and a vehicle capable of functioning without repair from Earth. Farther outward, those demands do not merely add together. They begin to shape the mission itself. The spacecraft becomes more independent. The crew becomes more self-reliant. The communication becomes delayed. The body becomes part of the engineering problem, and the distance stops being something outside the vehicle. It enters the design of almost everything inside it. Once distance enters the design of everything inside a spacecraft, another pattern becomes easier to see. The solar system does not ask only how powerful an engine is, it asks when you leave. Planets move through repeating arrangements around the Sun, and those arrangements create opportunities that open and close on schedules set by orbital mechanics. A launch window is not simply a date chosen by engineers. It is a period when the positions of Earth, the destination, and sometimes other planets allow a useful trajectory to exist. Mars offers one of the clearest examples. Roughly every 26 months, Earth and Mars return to an arrangement that supports an efficient transfer. Miss that opportunity, and the next one is more than 2 years away. For the outer planets, the timing can become even more restrictive. Some missions use gravity assists from several worlds, and those worlds must appear in the right sequence at the right times. Voyager 2 benefited from a rare arrangement of Jupiter, Saturn, Uranus, and Neptune that allowed one spacecraft to continue from one giant planet to the next. That alignment was not created for Voyager, it was simply there. Human beings noticed it, built quickly enough to use it, and launched before the geometry changed. The spacecraft then spent 12 years traveling from Earth to Neptune. This is one of the quieter ways distance shapes exploration. It does not only determine how long a mission travels after launch, it can determine how long people must wait before launching at all. And once a spacecraft departs, the calendar continues to expand. A mission to the outer solar system may spend close to a decade in development before it ever leaves Earth. Transit can consume another decade. Orbital operations may continue for years after arrival. Scientists can spend additional years interpreting the returned data. From first proposal to final research paper, one mission can occupy a large portion of a professional life, sometimes more than one. People who help define the scientific questions may not be the same people who receive the last measurements. Engineers who begin designing hardware early in their careers can be approaching retirement. When the spacecraft finally reaches its destination, graduate students can become senior researchers while the machine is still traveling. The solar system makes long projects feel almost biological in duration. They grow alongside the people who build them. This helps explain why Uranus and Neptune remain so incompletely explored. It is not because they are uninteresting. Uranus is one of the strangest large planets we know, with its extreme axial tilt, unusual magnetic field, low internal heat flow, narrow rings, and complex moons. Neptune has the fastest measured planetary winds, an active atmosphere, a powerful internal heat source, and Triton, a captured moon that may preserve clues to the distant Kuiper belt. There is enough science at either world to occupy an orbiter for years. The difficult question is how to send one. A mission must compete for funding with spacecraft bound for Mars, Venus, Europa, Titan, asteroids, comets, and the Moon. It must fit within launch opportunities. It must survive the long transit. It must carry enough power to operate where sunlight is weak. It must communicate across billions of kilometers. And because returning is so difficult, reliability matters in a special way. If an instrument fails on a library bench, it can be repaired. If a spacecraft fails near Neptune, no technician is coming. A replacement might require another decade to design and build, followed by another long crossing. For the outer planets, failure can cost not only money, it can cost time, measured in generations of researchers. This is why mission planners often appear conservative. Systems are tested repeatedly. Components are duplicated when possible. Software is designed to recover from faults. The spacecraft is expected to continue working after years of radiation exposure, thermal, cycling, vibration, vacuum, and long periods when no person can touch it. Distance rewards patience before launch because there may be no second chance after it. There are ways to shorten some journeys. Chemical propulsion is not the only method available, and engineers have studied alternatives for decades. Electric propulsion has already become common on many robotic missions. It produces very little thrust compared with a chemical rocket, but it can operate efficiently for long periods. Instead of one brief, violent acceleration, a spacecraft can receive a small push for weeks or months. For some missions, that changes what trajectories are possible. Nuclear thermal propulsion offers another possibility. In such a system, a reactor would heat a lightweight propellant such as hydrogen and expel it at high speed through a nozzle. Because the exhaust can move faster than in many conventional chemical engines, the same amount of propellant can produce more useful change in velocity. The United States tested nuclear thermal rocket engines during the 20th century, but none flew in space. Modern programs have returned to the concept because faster crewed travel could reduce some of the risks that grow with time. If a Mars crossing becomes shorter, the crew spends fewer months exposed to interplanetary radiation and reduced gravity. If travel to Jupiter becomes shorter, the same principle applies on a larger scale. Faster transportation does not make the planets closer. It changes how long we must remain between them. Farther ahead are propulsion ideas that remain much less mature. Fusion could, in principle, provide very high exhaust velocities. Concepts based on advanced electric systems, beamed energy, or other methods might also change. Whilst the way spacecraft move through the outer solar system seems set, but there is a wide distance between a physical principle and a dependable spacecraft engine. A reaction that works in a laboratory does not automatically become a propulsion system that can operate continuously for years. A future engine must produce useful thrust, reject waste heat, survive vibration, carry or obtain its fuel, remain controllable, and operate with extreme reliability far from repair. The solar system has a way of turning elegant equations into engineering. Even if engines improve dramatically, one boundary remains unchanged. Communication still moves at light speed. A spacecraft might someday cross the distance to Neptune in a fraction of Voyager's 12 years. Its radio signal would still need hours to return. That distinction gives future exploration an interesting shape. Transportation may become faster. Isolation will remain. A crew could arrive sooner while still needing to make decisions without immediate help from Earth. Robotic spacecraft could move quickly between destinations while remaining separated from their controllers by long communication delays. The solar system might become easier to cross without ever becoming small. And perhaps that is already true in another sense. During the last few decades, robotic spacecraft have made distant worlds feel visually familiar. We have seen dunes on Titan. We have watched storms move across Jupiter. We have traced fractures through Europa's ice. We have looked into the blue atmosphere of Neptune and across the cratered face of Triton. Images compress distance remarkably well. A picture from billions of miles away can appear on a screen in front of you at the same size as a photograph taken across a room. The physical separation disappears from the image. What remains hidden is the journey required to obtain it. Every close view of an outer planet began as hardware on Earth. Metal was shaped, circuits were assembled, instruments were calibrated. A launch vehicle lifted the machine from the ground. Then, for years, it traveled through a volume of space where almost nothing happened that a person could see. The mission became waiting, The spacecraft crossed the distance whether anyone was watching or not. And eventually, a signal returned carrying a new landscape. This is how our map of the solar system has been built. Not all at once, not from one perfect view. It has arrived piece by piece, often separated by years. Mercury required repeated encounters before a spacecraft could remain there. Venus allowed us to reach it quickly, but resisted long survival on its surface. Mars turned distance into launch windows and delayed conversation. Jupiter introduced a planetary system inside the planetary system. Saturn stretched missions across decades. Uranus and Neptune showed what happens when one brief encounter must support scientific questions for generations. The farther we travel, the more distance becomes something other than mileage. It becomes timing, it becomes autonomy, it becomes memory. And somewhere beyond the final planet, the same scale continues outward into regions where even the longest planetary journeys begin to look small. Beyond Neptune, the word planet stops being the best guide to distance. The Sun still has companions out there, but the pattern changes. Instead of another large world waiting in a wider orbit, there are populations of smaller bodies spread through the outer reaches of the solar system. Some belong to the Kuiper Belt, a broad region of icy objects beyond Neptune. Farther still, the gravitational domain of the Sun may extend into the much more distant Oort cloud, a population inferred from the paths of long-period comets. By then, 30 astronomical units no longer feels like the edge. It feels like the beginning of the outskirts. Neptune itself circles the Sun at about 30 astronomical units. Pluto follows an orbit that carries it through a more distant part of the same outer region. Beyond these familiar names, the distances keep expanding until the scale used for the planets begins to lose its usefulness. An astronomical unit is convenient because the planets live within dozens of them. Interstellar space does not. The nearest star system lies more than 4 light years away. A light year is the distance light travels in 1 year, so the nearest stars are separated from us by distances that make even Neptune look close. This comparison changes the meaning of everything inside the planetary system. A spacecraft taking years to reach Saturn, or more than a decade to reach Neptune, seems slow when measured against a human life. But those journeys are still small enough that we have completed them. Machines built on Earth have crossed those distances, sent back images, measured atmospheres, sampled magnetic fields, and continued operating while their signals took hours to return. The planets are difficult to reach. They are not beyond reach. That distinction may be the most important scale in the entire journey. Between Earth and Neptune, the problem is severe but recognizable. There are launch windows to calculate, propellant to carry, radiation to manage, power to generate, communication delays to accept. Machines can be designed around those constraints, even when the design requires decades of work. Between the Sun and another star, the same methods become inadequate. A spacecraft that is fast by planetary standards would need thousands of years to cross even the nearest interstellar distance. The problem is no longer simply a longer version of a trip to Neptune. It becomes a different class of journey. That makes our planetary neighborhood both larger and smaller than it first appeared. Larger because each orbit contains more empty space than a classroom diagram can show. Larger because a planet that looks adjacent to Earth on a page can require months or years to reach. Larger because every mile of separation carries consequences for communication, biology, energy, and time. But smaller too, because all 8 planets remain clustered close to one star compared with the distances between stars. The entire world of planetary exploration exists inside that contrast. From Earth, the night sky compresses it. Venus can look like a bright lamp near the horizon. Mars can resemble a reddish star. Jupiter may be brighter than almost anything around it. Saturn can be found as a steady point. Uranus is barely visible to the unaided eye under ideal conditions, and Neptune requires optical help. They all appear on the same dome of sky. Nothing in that view tells you how long the crossing would take. The eye receives direction. Physics supplies distance, and distance is not only a number placed beside a planet's name, it determines how much of a spacecraft must be fuel and how much can be payload. It determines when a mission can leave and which worlds can be used for gravity assists. It determines whether engineers can react to a fault in minutes, hours, or only after the spacecraft has already protected itself. It determines how long a crew must live inside a closed system. It determines how much radiation reaches them before arrival. It determines how much food must be carried, how much water must be recycled, how many spare systems must survive, and how much independence the people or machines on the journey must possess. Distance becomes architecture. It becomes schedule. It becomes the interval between a question and its answer. Planetary science has learned to work inside those intervals. A spacecraft may spend years crossing empty space for a few hours of observation. Another may remain in orbit for more than a decade, sending its discoveries home, one delayed packet at a time. A mission can end while its final signal is still moving toward Earth. None of this makes the solar system inaccessible. It simply makes access slow enough that patience becomes part of the technology. The instruments are built from metal, glass, silicon, insulation, propellant, and software. The mission is also built from time, years of design before launch, years of travel after it, years of science after arrival, years in which a distant world continues moving around the sun, whether a spacecraft is there to watch it or not. This may be why a map of planetary distances can never fully describe the place we live. A map gives positions. A mission reveals relationships. Earth is not the stationary starting point. The destination is not a stationary target. The sun is not a marker in the middle. Everything is falling through gravity, moving around everything else, carrying its own momentum into every possible journey. To cross from one planet to another is to join that motion with precision. You depart one orbit. For a while, you belong to neither world. Then, if the timing and energy are right, another planet arrives at the same place you do. That is what reaching a planet really means. Not overcoming the distance, meeting it. And after all the changing numbers, the launch windows, the years of transit, and the hours required for a signal to cross the outer system, the original diagram can be seen differently. The planets are still arranged around the sun. Nothing about that basic picture was false. It was simply missing time. Add time and the dots begin to move. Add motion and distance begins to change. Add a spacecraft and the empty spaces become trajectories. Add a radio signal and those trajectories become delays. Add a human body and the delays become exposure, supplies, isolation, and endurance. The simple map becomes a living mechanical system, and from here on Earth, all of it continues whether we measure it or not. Mercury moves quickly through the sun's glare. Venus follows its shorter year. Mars falls behind and is caught again. Jupiter carries its moons around a much wider path. Saturn turns beneath its rings. Uranus continues through its decades-long seasons. Neptune advances almost imperceptibly along an orbit that outlasts a human lifetime. Each world is somewhere different now from where it was when this journey began. Earth is too. The distances have already changed. The planets keep moving.